Pavana, please start.
Hello. Hi, everyone. Welcome to my presentation. Today, I will be presenting a recently published paper on ICLR entitled Fed-Babu toward enhanced representation for federated image classification. The authors are mainly from the Korean AI Institute. Here's the brief agenda for today's presentation. I will first introduce the motivation and background. Then I'll talk about the core idea of the paper, which is called Fed-Babu. Then I'll talk about some experiments, and finally, I will conclude the paper. So federated learning, as we know, is a very important machine learning paradigm these days, mainly because of the many advantages that it offers, especially the data privacy. For example, the several clients which participate in the training can come up with their own data set. The data set does not have to be shared with the server, but just using a model updates or some aggregates, the updates can be aggregated on a server and you can jointly train a common global model. So this is the main goal of federated learning. So the primary stages of training includes the local update stage, where the local training happens on the device using the global model that is shared by the server. And the other stage is the aggregation stage, which happens at the server, where basically all the updates from the clients are averaged. And the training process continues in this way. So the main standout point of federated learning compared to distributed learning, for example, is the data heterogeneity. So because different participants come with their own data sets, the distributions of their data may need not be in the same domain. They could be non-IID data. So this data heterogeneity is the main underlying principle of federated learning. While this is a very important thing, this can also act as a curse, mainly because all the devices come together to jointly train one single global model. Because they have their own data sets and the local training happens with their own data, there's a possibility that the convergence will be slower and this model may not be completely optimum sometimes. And if you, especially when you want to personalize the models, and if you want to have models that are pertaining to a particular local client and their own data, if the client wants to use the final output, that is the final global model for their own purposes, it may not be completely optimum. So this data heterogeneity can act as a curse. On the other hand, if instead of having one single global model, if we can tweak this to multiple personalized models, personalized according to every client's requirements and their own data, this data heterogeneity can act as a blessing. So there is these two aspects when it comes to data heterogeneity and when it comes to federated learning with personalization. So while we have a lot of papers that focus on either of it, one on the main federated learning and several optimization methods in that, the other hand, we have several personalized federated learning papers which talk about how we can get these multiple models to work. But the problem statement that this paper focuses is on how can you have both of best worlds. So one is you have a single global model which can be tweaked to personalize multiple personalized models without expending a lot of computation power or without expending a lot of resources. So this is the main problem statement that this paper focuses on. So before we go into the solution part, let me introduce some more background on this. There are certain observations that is made before the main idea is presented. One is, let's say, how a single global model can be personalized. So let's look at how effective a single global model can be. We can take the example of federated averaging, where we have the trained global model. And what we do is we try to complete the training. We have one trained global model. And after that, that is broadcasted to all the clients. And they are personalized within the clients with a few more epochs. So in this example, the authors take MobileNet and they train the data set used for training is CIFAR10 on 100 clients. And these are some of the parameters. You have a client fraction which takes part in the training, and tau is the number of local epochs, and S is the shards per data because they want to highlight the data heterogeneity. They split the model in a way that each of it get different shards. So if you have more shards, which means that it is less heterogeneous because there are more number of classes given to every client. On the other hand, if you have smaller number of shards, it implies that you have higher heterogeneity. So the plus or minus, the number you see here is nothing but the mean and standard deviation of the accuracies of all the clients. So the initial accuracy here is what can be seen of the actual single global model. And the personalized is nothing but After the whole training is completed and the global model is given to all the clients will take this and do some kind of fine tuning or some extra 5-6 rounds of few more epochs of training on their own training data set. And that's how we try to compute this personalized accuracy. So if we can see in the table, we say that this initial accuracy is a lot less than the personalized accuracy when it comes to without the fine tuning part. As the heterogeneity increases, we see that the initial accuracy is very worst compared to smaller heterogeneity, but the personalized will be much better. So the implication is that if you have a single global model, it probably is not as effective to personalize it as is. So you cannot really train one single global model and say that, hey, you know what, you can take this as your personalized federated learning model and the clients can use it for their own use. It will not really be effective because the accuracy will be really bad. But on the other hand, if you take these models and try to run some more training locally on the device at the end before the inference happens, it'll be a lot better. So this is one observation that this paper brings out. The second observation is about how the data sharing can have an impact on the whole personalized federated learning aspect. So for that, let's assume that we try to pass some portion of your non-private data set from each of your client to the server. So that is represented by P over here. So let's say that the server has some amount of data and it uses that knowledge. And then we continue the same training as before. We try to look at the final accuracy, which is called the initial accuracy. And then we try to run some extra fine tuning steps on the devices for different shards. And that will be called as the personalized accuracy. So here we see that the accuracy actually keeps going down as the heterogeneity increases when you have a lot more data. So which means that the more data information that the server can have, and if you do a lot of aggregation using that, it means that your initial accuracy, that is your global accuracy, will be very good, but your personalized accuracy will not be that great. It'll probably just keep dropping. So the second observation is that having data sharing is like really important because sometimes there will be a lot of unnecessary information when you do when a lot of data is shared with the server. So that can also kind of lead to poor performance in the personalized federated learning performance. And yeah, so basically it's that boosting, if you kind of try to emphasize training your single global model, if you try to boost the performance of the single global model, it can hurt the personalization. So while the data sharing increases your overall initial accuracy, it keeps decreasing your personalized accuracy. So what we can do is we can kind of narrow the update parts so that the degradation problem is kind of remedied significantly. So for that, we talk about something called as head. So the observation is that the head can deteriorate the personalization performance because the head is very biased. So what is the head and how exactly is the role played in this federated learning? Let's look at the actual neural network layers. So here, let's consider an example of a general convolution neural network. This is the overview of it. You have the input going through all the convolutional layers. So the whole light green that is highlighted can be treated as your feature extractor because the role of your lower layers of your convolution layers is basically to do the feature extraction. These can be called as a generic knowledge layers because they are very generic, as opposed to going towards the end of the neural network layers. You have your fully connected layers like your softmax, etc. It depends on what all layers you have at the end, which basically play the role of classifier. So from there on, you give the output. So which means that the classifier are very task specific. So they have knowledge specific to your task. So they have a lot more knowledge, which is the reason why we were calling it to be biased. In the previous slide, we were calling the head to be biased because it is very specific. It has very specific information to do the task that you are given according to the data that you trained on. So this is what the head constitutes of. So we're talking about probably the most famous CNNs like ResNet or MobileNet. We can see that they usually have one linear layer at the end of the model. So now this linear layer can be counted as the head. So this head, what exactly it does in terms of the learning or in terms of your whole training aspect is, it is like your decision boundary. That is what does the decisions. And all the other layers which comes before the head, except the head basically, can be called as the body. they basically do the representation learning because they do the feature extraction, they have the representations, and they're very generic knowledge layers. So keeping this whole knowledge of head and body in mind, let's just go to the next observation. So the third observation that the authors see is that now we know we have a head, body, and a full neural network. And they take an experiment on Cypher 100 on mobile net again, and they train for the 160 total epochs. This experiment is not related to federated learning at all. It is basically a centralized setting where you have like a single a client, a single model that you're working on. And the full over here that is represented in blue, which means that the full training was done on all the layers. So the accuracy, this on the left is the test accuracy on the y-axis. The test accuracy was computed when the training was done on all the layers. And the red means the body, means we separated the head and the body, and just the body, that is the lower layers, did the training and we computed the test accuracy. And the green means the head, where the final layers, the one or the two or the fully connected layers that you have according to which CNN that you're using, the head was separated out, and it was trained separately, and then we computed the test accuracy on it separately. So from this, what we can see is the model, which was initialized probably, and the head was fixed, can almost have comparable performance as the full neural network. So basically, the head really does not have a lot of impact on your overall accuracy. You see that the accuracy probably is not changing much for the head at all. But if you train just the body, you see that it has almost the same performance as training the whole neural network. So this probably is not contributing to the accuracy part at all. So this is the third observation. So keeping these in mind, what this paper presents, FedBabu, the main algorithm, it basically is called federated averaging with body aggregation and body update. So we basically focus on the body. So we try to decouple the whole network into two parts, the whole body, all the lower layers, and then the head. So two parts. So the body can be called as the extractor also because it does the feature extraction. Now, all the training is done on that basically for generalization because it has a general knowledge of the network. Now, this thing can be related to some universality, like, main performance, overall performance. And the head can also be called as a classifier because, we can train it for doing more specialization tasks because it has a very task-oriented knowledge that it has. So this can also be called as, this can be related to personalization. So when it comes to federated learning, this kind of acts as an advantage to us because this personalization is what we want to do at the end. According to our previous observation 1 and 2, we saw that having a single global model was good, but later when it was fine-tuned, personalization was even better. So that way, this whole BABU, the body aggregation, body update, is kind of merged with the federated learning, and FedBabu is formed where you do not train the head of the in the federated training phase. So basically, when you're developing the single global model that you want, you're not going to aggregate the head. You're just going to fix it. You're just going to initialize, fix it, and pass it to all the clients. All the clients will have the same head. We do not pass it to the server at every iteration. No aggregation is performed on that. At the end, when the training is completely finished, we take the final global model, broadcast it to all the clients. Now the clients will take and fine tune this head on their own evaluation process, and the personalization is formed. So pictorially, this looks something like this. On the top, you have the federated averaging. Let's take it as 3 stages. One is the broadcast where in the first stage, the initial global model is broadcasted, or in the later training layer stages where the aggregated model is broadcasted. So this is the broadcasting stage. Local update stage is where all the clients download this model, do the local training, the most important phase, and uploading it to the cloud server. And the final phase, aggregation, where the server receives all the updates from all the clients, it does the aggregation there. So these 3 stages. The bottom we see FedBabu, where the broadcasting stage is really common for both of it. You can see that the lines over here, the red and the blue black lines over here basically represent the decision boundaries, which are basically related to the head because head does the decision boundary parameters and things. And the shapes over here, different shapes you see over here, they indicate different classes. So in this example, they're considering every client to have 2 different classes. So in federated averaging, what happens is the federated averaging basically updates the whole network. like normal training. And during the local updates, on every client has a different classifier like this. And finally, they're all aggregated at the central server in this way. And as we can see, the heads are very different. The head of the central server, the heads of all the clients are really different. And we see that this kind of behavior is seen on the server when aggregation happens. As compared to FedBabu, what we do here is the broadcasting stage is the same. Because we fix the head, we do not aggregate the head. All the clients have the same head. You see the head is really fixed. The decision boundaries are different in federated averaging. Here, they predominantly remain the same. Only the representations are learned in every stage. The rest of the training, the rest of your SGD happens as usual, but just the parameters of the body. So now you have same classifier image. So classification boundaries are the same, but the classifier output will be different. And this is sent to the central server. So during aggregation, we see that this confusion of having different heads, aggregating it in this different direction, that doesn't happen because the head is really fixed. So all we're caring about now is all the representation learning part. So the training can happen a lot, much better manner in FedBabu. Any questions so far? Okay. If not, let's go into the algorithm of the whole training procedure of FedBabu. So first of all, we initialize the global model, global parameter. The theta is nothing but the parameter of the model. And for every K communication round, we select a random subset of M number of clients, just as federated averaging. And each client in parallel will do the computation and come up with the local model. And how that happens is, let's see in the client body update. So in the client body update, what happens is every client will download the global model that was initialized by the server. And then it uses the batch size, it uses the data set size, and then it computes the number of iterations under the number of epochs and it performs the SGD. But mind you that now we have separate parameters. This is for the extractor, theta X is for the extractor, that is the body, and theta G0 class is nothing but for the classifier, that is the head. See, this is not changing at all. We're just using this as a reference to complete the training, and we compute the local body parameters. And then this is returned to the server. Now the server receives the model update from all the devices, which is basically just from the body. And it does the update, it does the aggregation, and then it returns the global model again. And this process keeps continuing. So once the whole training procedure is done, is when the update of the head happens. So once this is done, the server will send the global model to all the devices again. The devices will download it, and then they'll do some fine-tuning using their own data set on the global model. And each of them will come up with their own personalized model, which is much more accurate. And this whole process will be much more faster because of the observations that we just had. Okay. Next, I have some experimental evaluations of the whole process. So the experiment was conducted on MobileNet, where you have one single linear layer at the end, which acts as your classifier, and the rest of the layers can be treated as the body. And the whole experiment was performed on Cypher 10 dataset. They have 100 number of clients, and each client has 500 training data and 100 test data. And the shards are split in such a way that they have such that this can be treated as a hyperparameter, which can be tuned. And you can set the number of shards, you can set the size of the shards according to the formula given, which is dependent on the data set size and the number of clients taking part in that round. And how many clients take part in a given round, that can be tuned. And what is the number of local epochs you have for your training, that also can be tuned. Also the number of shards per user, which determines the heterogeneity, can also be tuned. And the other two metrics that we're using is the initial accuracy and personalized accuracy, like we already saw in the previous slide. So basically, initial accuracy is the learned global model, which is broadcast to all the clients at the end of the federated learning training, is evaluated on the test data set of each client before doing the fine tuning, just computing the accuracy based on the test data set is the initial accuracy. And personalized accuracy is after all the clients receive this model, they do the fine tuning or some more local training according to the client's training data set. And then after the fine tuning is finished, they use their own data set, test data to check the accuracy, and that can be counted as the test personalized accuracy. So these two are the main metrics that we'll be seeing today. And this whole experiment was performed as a simulation on Titan RTX. So there are 5 different observations, that experiments that was done. The first one is to check the representation power of a single global model. In this, we look at mainly federated averaging and the proposed method FedBabu, where the training is done with the head or without the head, and then the training is done as per their own algorithms, but then the test accuracy is done either with the head or without the head, whether fine tuning is needed or not. And according to that, we see that FedBabu without the head, which is the main proposition, is a lot more accurate, and it has improved representation power under really large data heterogeneity. So as the shards decrease, which means that data heterogeneity increases. So in this higher data heterogeneity case, we see that the accuracy is much, much higher, which is a more practical situation in federated learning, where you have a lot more participants, and you have a lot more data heterogeneity. So we see that FedBabu performs pretty well here. And then the second experiment was to see what is the personalization of FedBabu. And in that, we see that there are different settings of changing the shards, changing the local epoch training times to see how the behavior is. And for the update part, which is the personalization, which means that the whole training is already completed. We have the global model, which is already broadcast to all the clients. What happens after that? So when we measure, when we do the fine tuning or the personalization on the clients, what is the effect when we do it for the whole body, or just the head, or the full, including the head, or doing the whole neural network fine tuning? FedBabu versus Fed averaging. And here we see that no matter what part of the neural network you choose to fine tune or to do the update for personalization, we see that the proposed method has much higher accuracy. In fact, with higher data heterogeneity, it shows even much better performance compared to any other cases compared to the baseline. And also, this can also kind of imply that the computational cost can be reduced by fine tuning only the head, if you want, without degrading the performance. So it is really not necessary to fine tune the whole thing. You can just fine tune the head and still attain a lot better performance. So this is a bigger advantage. And other is to check several other baselines. We only saw Fed averaging and incrementally how that worked for FedBabu. Now let's look at all the performance comparison with several state-of-the-art personalized federated learning methods. Again, we look at personalized accuracy, the metric where the fine-tuning happens and things. And we again have different hyperparameters that we determine the data heterogeneity, determine how many participants are taking part, and what is the local epoch number, etc. And again, we see that FedBabu outshines all the other competitive methods that we have. In every scenario, we see that this works very, very better compared to all the other baselines. And the fourth experiment that this performs is to see what is the speed of personalization. So all the advantages we were seeing so far was on the accuracy perspective, that how much more accurate this proposed method is. Now let's look at what is other advantage it offers. We can see that the speed of personalizing and the performance according to the fine tuning also is a lot better for FedBabu compared to federated averaging. So for example, let's consider 2 different scenarios where the data heterogeneity is less and then more again. And the highlighted block shows that FedBabu actually outperforms federated averaging again. It shows much better accuracy. It also achieves this better accuracy with minimal fine tuning compared to federated averaging. So for example, in the case of the first scenario, federated averaging takes about 20 epochs to attain, about 40.86% of accuracy. But FedBabu takes nearly like much less. It takes only about 2 epochs of fine tuning to attain that performance. Again, even in a higher data heterogeneity case, we see that federated averaging shows worse performance as as is for the accuracy, it really drops because of federated averaging does not work that great when there is a lot of heterogeneity. But FedBabu already outperforms there. And again, if you have to look at how faster this accuracy was reached, for example, let's take 63% so. Federated averaging takes about 10 epochs, but then FedBabu takes only about 1 epoch. So this is way faster compared to the federated averaging too. And the final comparison it does is, so far we only looked at federated averaging and the body update and body aggregate using the FedBabu. The authors also wanted to see how they can proximally change, use different algorithms as a base, and then implement their own BABU on top of it. And they used FedProx, which is a very state of the art for dealing with heterogeneity, data heterogeneity, especially in federated averaging. So they used the same thing. They used their proximal term mu, and they set a value which was according to the paper, which was set according to the paper. They used the same settings. And again, we see that personalized version of Babu with FedProx works way higher. The accuracy is much better no matter what level of heterogeneity that you choose. It's especially better when you have a lot of heterogeneity. Personalization is much, much better. So these are all the experiments that the paper conducted. And overall, we can see that personalization is much better. The accuracy is much better, and the whole personalization happens much, much faster compared to several state-of-the-art personalized federated learning methods. So I will finally conclude the work. So the paper does has three main contributions. Firstly, they investigate the connection between a single global model and a fine-tuned personalized model. They do this by analyzing the whole federated averaging algorithm at the client level, and they show how the training the head using the centralized data has a negative impact on the personalization. And they also demonstrate that if you have a fixed random classifier, that is, if you fix the head, it can have a really same or similar comparable performance as a whole learned classifier as versus using the whole neural network for the training. So this difference was also demonstrated by this paper. And keeping these observations in mind, they proposed a novel algorithm called Babu that basically reduces the update and aggregate parts from the whole model to the body of the model during federated learning training. And they also show that this is very efficient, especially in several high data heterogeneity conditions. And to show more adaptability of their algorithm, they try to merge this with some regularization-based federated learning algorithms such as FedRox. And they show that even despite using a different method as the base, this algorithm still outperforms the base algorithms and the original algorithms, and it still is faster, but performance is better, and it is also still more efficient. So this is all I have today. Open to any questions. Thank you for listening.
Pavana, very interesting work.
Yes.
So for the evaluation, it seems that the paper has not compared with those personalized federated learning paper. It's like the baseline or something like not like the coverage is not it somehow is limited. Okay. Let's see. So they have the Fed per. I remember there's another paper using some. Let me see some envelope.
The module.
Yes. Which one is that paper?
I don't think they compare it with that because that is more meta. Okay. It uses meta learning, right? Yeah.
Is that paper too old? So they don't.
No, actually, they use meta learning to do to develop the module envelopes for comparison, right? And I think this paper was trying to focus more on federated learning alone with personalization. So that's why I think they didn't count the paper that you just mentioned.
So the high level idea is trying to freeze the head of the model, but using the remaining model layers to learn the presentation of different heterogeneous data, right?
Yes.
And they will share the representation part, so they can build a common space to represent those heterogeneous data. Then they're
Yes.
using their own head to do the classification, right?
Yeah, yeah, to fine tune the classification. Yes.
Okay. Do they have any theoretical analysis? Say why?
No.
Uh-huh.
Yeah, actually, they don't have a theoretical support. I was looking at their open review. I think a lot of reviewers asked the same question, and they said that they probably will include that in the future work, but they just try to do the empirical evaluation for now.
We submit a very similar idea paper, but was rejected by, I think, by ICML. Like we are trying to do more fine-grained representation. So they only, basically here they only do just like presentation of the data, right? We wanted to select the common representation of the data and some personalized representation of the data. We try to separate. So if we can represent the data into some embedding vectors, we try to separate the common part and the personalized part. But one of the key weaknesses, we don't have a theoretical analysis.
Okay.
Yeah, but this paper, I mean, the idea is very intuitive.
Yeah, I think your idea is really interesting. Maybe I think ICML tries to ask for more theoretical support. I think ICLR that way, at least this year and last year, I say that they have a lot of more papers which do empirical study only without much support with the theory, and they still get accepted.
Okay. Okay.
Yeah, I think it's just the conference.
Okay, thank you. I have no more questions.
Okay, thank you.
Pavana, I share the same comments with Dr. Wang. I mean, many personalized file learning paper, right? So I think here, FedPer 2019, that one is a personalized one, right? For the rest of them, I don't know. I think some of them is kind of training the global model. I think they should compare with more personalized for learning algorithm and designs as well. For example, I think Dr. Wang want to mention probably the paper of Li, the share the mask, right? I mean, they do the mask updates instead of do the gradient updates, right? That's also used for personal file learning. So
okay, go ahead.
No. I mean, do they? I think the comparison is a little bit I don't know, it does not cover enough, I think.
Okay, so I kind of agree with what you're saying, but I think the explanation that the authors give is that one is I think this last 2 years we've seen a lot of work in federated, the personalized federated learning front, right? So they chose out the ones that are most similar, that have a lot of overlap with their own paper. So if you look at excuse me, the FedPer, LG Fed, like basically all these baselines that they have, right? They all kind of deal with the same concept of head and body, and doing the aggregation of one part, doing the classification using another. So some kind of overlap is there in all of these works. So I think that's the reason they chose only these works, because they're most closest to their own work, as compared to the one that you mentioned, Li's work, or probably what Dr. Wang mentioned, the module GitHubs, which is the most popular the personalized paper. Yeah, I think that's why they didn't use that, but just these.
But in terms of personal file learning, I think people doesn't care about, if it's similar to your design or to my design. As long as it works, and for personal training models, the accuracy is good. I mean, it's better, then people will prefer the algorithm, right? So I think we discussed this before. It's not like the general file learning. Somehow you have a benchmark, a standard, right? over there.
Right.
Personalized one, it
I
doesn't matter
think
what you use. Yeah.
I think that way you see the per Fed average, the
Mhm.
personalized Fed average in the 2020 paper. I think that's like the most popular. I think it
That's the
has
most
more
popular
citations.
one.
Yeah, they have those the local objective with special hyperparameters. I think we discussed this paper before. Yeah, I think this is actually the most popular one, and it is actually not having the similar idea as this paper. They have a different idea, but it's still a different federated, personalized paper. So I think it just is about how do you know which all to choose to compare, right? Because especially if you have a lot of papers, it's like you don't know which one to compare with.
Mm. So for the federal REP representation one, that one is personalized or it's a global one? 2000.
It's personalized.
Okay.
Yeah. It's like it does the aggregated representation and it learns only the body and its own head. And in one single epoch, it tries to update the head or something like that. So that also is perceived as the personalized. A little bit personalized, yeah. But again, it has the same concept of head and body, the dissection.
Okay. Well, I think if we try to, any of us try to write a personalized learning paper, that's a question mark, right? So
Yeah.
there are too many personalized learning design in recent 2 or 3 years. But
Yeah.
which one you should choose, right? So
Yeah, there's like no benchmark. I think for federated learning that way, we know Fed average, Fed broad,
yeah,
scaffolded. Yeah, but yeah, there's some at least that are very popular that we can. But yeah, your question is valid. But again, yeah, we don't know. There is nothing like the standard for personalized.
mhm. Okay. All right, thanks. Any other questions?